Okay, welcome to topic 3, branched substituted hydrocarbons and isomers. So this is a continuation of organic chemistry. If you did not watch part 1 and 2 or topic 1 and 2, then this you cannot do. So you're going to need to go back and make sure you complete those, take a photo of your notes, and make sure you turn it in so that I can actually give you credit for it. So some of you are not doing that. You're just kind of jumping into the assignments. I need to see the notes. I need to see that you spent the time, and I'm giving you credit for spending the time going through this. Okay, it's part of the assignment. Okay, so what we're going to do in here is we're going to take our general alkene, and alkynes, and we're going to add to them. We're going to add layers to them. So there isn't a lot of slides in this, but there's going to be a lot of an explanation, a lot of drawing. And so I'm going to show you kind of what we do when we branch off. So if you notice right here, we have carbon 1, 2, 3, 4, and 5. And right here, we have a little bit of a, oh, this is not working. Right here, we have a little bit of our branch. Okay, so what should be in this position? There should be another H, and there isn't. So we have a CH3 there, and we're going to see how that happens. You'll notice that the name is different, and the name is different. You should see numbers now, and you'll see YLs. We're going to get into all that, and for this one as well, you'll see this is the main branch, the parent branch, and this is going to be what we call the substituted or the side chain. Okay. So let's get to it. So structural formulas of alkenes. So alkenes are what we're going to focus on, but we can also apply this to an alkyne. All right, the first thing that we're going to do before we talk about the branching is we're going to talk about what an isomer is. Okay, iso, remember that phrase, like isotopes, right? It means the same. So something's going to be the same. So you'll notice molecules with the same molecular formulas but different structural formulas. So what is a molecular formula? A molecular formula is like C6H12. Okay, so super important that you kind of see that and you understand that. And the structural formula is what it looks like. So we're going to be able to draw different things. So we're not going to always draw the same structure for that molecular. What we will know from the molecular, though, is what family it belongs to: alkene, alkyne, and some other things that might be helpful. So what we're going to do is we're going to learn how to name isomers that have the same molecular formula but different structure. And we're going to see how to kind of add something to this. So the first thing we do is look where the double bond is located. So we're going to move that double bond. Up to this point, we've just had you write it right at the very beginning. We're not going to do that anymore. We're going to move it around. In order to establish where that is, we're going to put a number that shows where that double bond is. If you have a triple bond, then you'll be dealing with alkynes. The rules apply exactly the same way. We're just going to be doing alkenes in this one. And then what's in parentheses here is super, super important, and we're going to come back to that. We're going to use the lowest number possible. Okay, so let's start with our first example, 1-pentene. This should be a little bit of a review here. Pent means 5 carbons. So what we're going to do is we're going to do 1, 2, 3, 4, 5. And ene means we're going to have a double bond. And now you'll notice there's a 1 here. Okay, so what that means is we're going to start numbering our carbons. We typically start from left to right just because it's easier, because that's how we read. But it doesn't have to go left to right, okay? So we're going to change that. You need to be flexible with the fact that you can read from left to right or right to left. But because we're creating this structure, we're going to keep things simple. So that means on carbon 1, right, we're going to put an ene in there. And what does an ene mean? An ene means that we have a double bond. And so you'll notice I put a double bond right off of carbon 1. And yes, it is touching carbon 2, but that's okay, right? So carbon 1, boom, I see a double bond. Now we're going to put in our hydrogens. So we have 2 bonds there. So I'm going to put 1 here. And I'm just choosing to put it on the bottom. It doesn't matter. I could have put it on the left. Carbon number 2 has 1, 2, 3. So I only need 1. Carbon number 3 has 2, so I need 2 more hydrogens for 4 bonds. Carbon number 4 needs 2 more hydrogens. Carbon number 5 needs 1, 2, 3. Okay. Now that's what one pentene looks like. It shouldn't look any different than what we did when we were learning it in the last topic. All right, let's do a quick count and figure out what its molecular formula is. So there are 5 carbons, so C5, and then let's look at our hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we'll do a quick count and we see 10 hydrogens. That's a really good skill to have. Just stop and count everything. That's going to also show you, hey, this fits into the CnH2n general formula, which means it's a alkene, which we knew. Okay, so now let's look at 2-pentene. So 2-pentene is going to be taken the same way. So pent, we're going to do 1, 2, 3, 4, 5. The ene means we're going to do a double bond. Where is that ene going to go? Well, we're going to put it not on carbon 1, but now we're going to put it on carbon 2. And so it hits carbon 2 and carbon 3. And so now when I do this one, I've just shifted over the double bonds into the center of the molecule. So we have now hydrogens that we need to place. So this one needs 1, 2, 3. The second carbon already has 3, so we just need 1. This one has 3, so we just need 1. This one has 2, so we need 1, 2. And this one has 1, so we need 1, 2, 3. Okay. So that's what 2-pentene looks like. Okay, let's count everybody up. 1, 2, 3, 4, 5. So we have 5 carbons. And we have how many hydrogens? We're going to have 10 hydrogens. All right, so C5H10 is the same for both of them. Those are the molecular formulas, but you'll notice the structure is different. So what's so special about the structure? Well, the structure is different, therefore it makes it behave different chemically, physically, in so many different ways. Even though they're related, they're not the same. And so that's extremely important to understand about an isomer. And this is what makes organic chemistry such a large area to understand, because you have just these slight differences that can cause the molecule to behave extremely differently. Okay, so same molecular formula, different structure. All right, now let's go to 3-pentene. Now 3-pentene, we're going to utilize this last little parentheses here, use the lowest number possible. And we're going to try and figure out what that means. So I'm going to draw you a structure, and we're going to go about our way as though we're normally doing this. So pentene, so we have 1, 2, 3, 4, 5. The ene is a double bond, and it's going to be on the 3rd carbon. All right, so just like we did before, we have carbon number 1, 2, 3, so that means I'm going to put it right here. Okay, if I draw my hydrogens, I'm going to have 1, 2, 3, so hydrogen, hydrogen, hydrogen. Over here, I'd have 1, 2. On this one, I'm going to have 1, 2, 3, so I need 1. On this one, I'm going to have 1, 2, 3, so I'm going to put 1. On this one, I'm going to need 1, 2, 3. Okay, so now you might be wondering, well, let's do this too. C5H10. Now, how do I know that? You're just going to count everything. Okay, so what's wrong with this, right? Well, it follows the path. Okay, so now I need everybody to make sure that you're understanding why this is actually not correct. Okay. These molecules, as we're drawing them, they are 2-dimensional. Okay, so what that means is that they are flat structures on a piece of paper. They don't exhibit the actual 3 dimensions and angles that they would be showing. They also aren't showing you movement. They're not showing you translation, rotation. If you remember from the TED-Ed video, these molecules are moving. And so they did a great representation of that when they were showing it to you. Okay. So I need you to envision this molecule. I want you to pick it up off the paper in your mind, and I need you to flip it, okay? When you flip it, it's going to look exactly like that. Okay, so Try doing that again. Lift it up off the paper and flip it. And when you flip it, you'll notice it's exactly the same. It's almost like they're a mirror image, right? They're exactly the same. So why is that a problem? Well, they're not isomers. It's not a different structural formula. We just chose to draw it the way we're drawing it, but that doesn't mean it's a different formula. So what I want you to do is I want you to always make sure that you're using the lowest number possible, okay? It doesn't matter what direction you start counting in. So let's look. Let's start counting. If I count in this direction, 1, 2, 3, 4, 5, then 100% I would say that that's 3. But if I start counting from the other direction, 1, 2, 3, 4, 5, take a look at where we see our first instance of a double bond. It's on the second carbon. This can't have two names. We can't call it 3-pentene and 2-pentene another time. So we have to come up with a rule, and the rule is to use the lowest number possible, with the understanding that these things are three-dimensional and they come up and off the paper and they can actually move. Okay. If this is still causing you some issue, I want you to kind of think of it this way. If you were looking at my face, you go, okay, yes, that's Mrs. Ferrioli. I'm going to turn around now. You'd be looking at the back of my head, but it's still Mrs. Ferrioli. You're just looking at it from a different angle, right? A different perspective, but we're still the same. I did not change. Okay, so what does that mean? That means this does not exist. There is no such thing as 3-pentene, because if you try to draw 3-pentene, it's actually still just 2-pentene. Okay, so if you need to stop and kind of listen to that explanation again, please do. We're going to move on to other examples. Okay, so our next kind of special grouping of alkenes is something called aromatic. All right, aromatic means that they are cyclic. So these are hydrocarbons that normally would be in a straight line, but instead we're going to make them into a cycle. So we're going to kind of make a ring of them. And what happens is they exhibit something called resonance. Resonance is when double bonds move throughout the molecule. Oh, I thought I had pressed that. So double bonds move throughout the molecule. So we're going to have these enes, right, in this next example that we're looking at, but it's going to kind of not be only in one place. Let me show you an example. Okay, so the one example that's super important in chemistry is called benzene. Benzene's formula is C6H6. And really, I know you're like, okay, I have to memorize that. If you go into organic chemistry, yes, and you won't have to memorize it because you'll be drawing benzene all the time. It is a basis of many, many, many organic structures. Okay, so how do we draw this? We're going to take 1, 2, 3, 4, 5, 6 carbons, and we're going to loop them together in a circle. Okay, we're going to double bond one set of carbons, single bond, double bond, single bond, double bond, single bond. Okay, so that's its structure. And then we're going to make sure that we look that each carbon has 3 bonds. So each carbon needs a hydrogen, and each carbon needs a hydrogen, and a hydrogen, and a hydrogen, and so forth and so on. So this kind of looks like a Ferris wheel almost, right? Okay, so what is this resonance structure? Well, it's basically saying that these double bonds and these single bonds really don't stay put, because a covalent bond is a shared bond. What's actually happening is it's almost kind of a blend of the double and the single, and it really doesn't only sit on one of those particular bonds, okay? Because we can kind of rotate this around, it's not just going to show up like that. Okay, because this is the basis of most organic chemistry, we've come up with a shorthand way of doing things, and most molecules we've done. If you watched the TED Ed video, he showed you a little bit about that as well. So we have each corner is represented by a carbon atom. So corner, 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 corner. So there's our carbons. You'll notice double bond, single bond, double bond, single bond, double bond, single bond, just like the drawing. And then it's understood, of course, in the chemistry community that all carbons have to have 4 bonds, and if you don't see another bond on there, there's a hydrogen on it. All right, and so what you're seeing is me recreating the drawing that's on the left. So the easiest way to do this is corner, 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 and then you get double, single, double, single, double, single. So that's one way of doing it. You notice I didn't do the doubles exactly in the same way because it doesn't really matter. I can rotate it any which way I want. Another quick shorthand way to show resonance is putting a circle in the middle. And that kind of shows you that it doesn't have to belong to one particular place. So this almost looks like a washer or a nut, like a nut and bolt kind of thing. Okay, so C6H6 is very, very, very specific, and it's just one that's kind of in addition to the basics of the alkenes, and alkynes that sometimes shows up. Okay, next. So let's get into some of this branching and the substituting that we saw at the very beginning. So what you'll notice is that hydrocarbons, right, can have other atoms or groups of atoms that are added to the main chain, right? We can call that main chain the parent chain, main chain. And that branch that comes off of the main chain, that branch is called an alkyl group. Okay, what is up with this alkyl group? Well, this alkyl group is made up of either alkanes, and it could be other things too, but primarily we're just going to stick to the alkanes. And what you'll notice is that we're calling it alkyl because it's not really an alkane. It has a hydrogen that's removed. And then that allows it to be able to attach it to the chain. Okay, so we have alkyl groups that correspond to the number of carbons, just like alkanes, alkenes, and alkynes. So an alkyl group, first one would be methyl. All right, so how many carbons are in methyl? 1. So we sometimes see it written in a couple of different ways, so I'm going to show this to you. So if I want to show a methyl group, instead of writing CH4, I would write CH3. And not only that, the other H, right, is not there because this gets attached to a main chain of another hydrocarbon. Okay, what's another way of showing this? We collapse everything and we just say CH3. Okay, so let's look at our first example, which is 2-methylpentane. So you're going to see a lot of what's going on here with the little side chains. So this is how we draw our compound. So our first thing that we look at is the ending. The ending is always the main chain, the parent chain. And so you always start there. You always start at the end. I know it's a little weird. So we're going to do pentane. Pent stands for 5 carbons. So 1, 2, 3, 4, 5. It's ane, so we're going to have single bonds all the way through. We don't have to worry about anything else. And then we have this 2-methyl. So this 2-methyl is basically saying, hey, on carbon 2, I want you to add this methyl group. Okay, so what's methyl? Well, methyl's CH3, so 1 carbon. And where are we going to put it? We're going to put it on carbon 2. Okay, when you draw molecules, you're allowed to place it on whichever 2 you feel. Okay, so what does that mean? Well, I'm counting from left to right because it's just easier for me. It's how I think. But if I wanted to count from right to left, right? So if I wanted to count from here to here, then this one right here would be my carbon 2. And that would actually give us the same structure because I could lift it off the paper and flip it and it would look like the one I just drew. So don't be afraid if you want to start from that end or that end. However, be consistent with yourself so you're not confusing yourself. Okay, so now we have put in a methyl. We have put in the pentane. Lastly, we need to finish off the hydrogens. So this carbon 1 has 1, so it needs 1, 2, 3. So you'll notice hydrogen, hydrogen, hydrogen. This hydrogen, yes. This is a hydrogen, yes. This is a hydrogen, yes. And then this has 1, 2. And this one's going to have 1, 2, 3. Okay. So you'll notice, just a quick review, the pentane has all of them. That H is missing, and instead of the H that you would normally right? So instead of the H that would normally be right here in this place, we've now substituted it with a methyl group. And so we call that 2-methyl pentane. Okay, let's keep going. Examples, examples, examples. All right. So what if we have an ethyl group? So instead of a methyl group, we're going to have an ethyl group. An ethyl group is going to have 2 hydrocarbon branch attached. So 2 carbons in this. So what is this going to look like? Well, that means we have 2 carbons attached to each other because that's what makes an ethyl. And we're going to have hydrogens all around. Oh, I didn't give myself room. All right. Bear with me. Sorry. Okay, so we have 2 carbons, and we're going to have hydrogens here, 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 here. And we're not going to have the last one because it's not an ethane. This gets attached to another whole main chain. Okay, so whatever that is. How do we collapse this? Well, just to make things easier, CH2, CH3. And so this is called a ethyl group. There's a propyl, there's a butyl. You might have heard isopropyl alcohol. Okay, that's where that's all coming from. So we're gonna learn kind of where those things are from. Okay, let's look at this example, 3-ethylhexane. We are going to take that hexane. We need to draw that first. Hex stands for 1, 2, 3, 4, 5, 6. All right, so hexane is 6 carbons. Next, we're going to look at the ethyl part. Okay, so the ethyl part means I'm going to have 2 carbons. It's 2 carbons attached to each other. Where am I putting them? They're going to be put on carbon 3. It's like an address. So I'm counting from left to right because that's what makes me comfortable. And I'm going to put right on carbon 3. I'm going to put a carbon here, and I'm going to put a carbon here. Why? Because I'm trying to make my ethyl group. And then I need to finish this off with hydrogens for it to be proper. Okay, so that's my ethyl. And then I also need some hydrogens on the main chain. You can't forget those. It will be incorrect if you do. So hydrogen, 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 hydrogen. Okay, this one already has 3. Carbon 3 already has 3. So we only need 1. This needs a 1 and a 1. And you'll notice even though these are close to each other, they're not attached. That's super important to understand. And this is a 1 and this is a 1. Because in reality, they're actually not near each other. They'd be moving around and twisting and turning. Okay, so what you're seeing, quick recap, right? I'll do another color. 1, 2, 3, 4, 5, 6. This is, oh, I left off a hydrogen. Okay, so 1, 2, 3, 4, 5, 6, and that gives us a hexane. And then this is my branch off the main chain. And so we call that 3-ethylhexane. Okay. Next, what if we have more than one side chain? What if we have more than one alkyl group? If we have more than one alkyl group, we're going to add some prefixes. If I have 2 of them, it's going to be called di, right? So dimethyl, diethyl, dipropyl. If I have 3, trimethyl, triethyl. If I have 4, tetramethyl, tetraethyl. We don't usually go into the 4s. We're going to do 2s and 3s, but it continues from there, and you have prefixes kind of on top of prefixes. But it does really help. There is a logical order to things. Okay, so let's do examples. We are still giving numbers to each one of these alkyl groups. It's extremely important that you do because everybody needs a place. Okay, so here's our first example. 2,2-dimethylhexane. We're going to start with the hexane. So hexane means we're going to have 1, 2, 3, 4, 5. I'm just going to put this over here, 6. So I have some room for the next one. So there's my 6. And it's got single bonds all the way through because of the ane. All right. Now, my next piece to this is going to be the 2,2-dimethyl. Okay, so let's take that. So methyl means we're going to have 1 carbon group, but there's going to be 2 of them, 2 1-carbon groups, not attached to each other because they're going to both be on carbon 2. All right, so how do we do this? So the first methyl group is going to be on carbon 2, and that's a methyl right there. So we'll do H, H, H. Okay. The other methyl, so that takes care of one, the other methyl is also on carbon 2. So remember, there's a position right below it. And so that gets an H, an H, and an H. And so you'll notice on carbon 2, which is right here, you have a methyl and then you have another methyl. You don't want to put those two methyls together. If you put two methyls together and the carbons are attached, that's actually an ethyl. Okay, we do not want that. So now my job is, I got to put hydrogens all around. I'm just going to put lines because at this point I'm getting into my structure. So I'm going to put 1, 2, 3. Please understand there's hydrogens at the end. Carbon number 2 does not need anything. 1, 2 for this one. 1, 2, 1, 2, 1, 2, 3. Okay. So that's a 2,2-dimethylhexane. All right, let's move over to this next one. It's also a hexane. So let's do this one. So we have 1, 2, 3, 4, 5. Let me put this here. 6. Okay, so same thing, single bonds, hexane. Now let's look at the add-on, right? So dimethyl, but now we're doing a 2, 3. All right, so 1, 2, 3. So that just helps you number it. We're going to, on carbon 2, we're going to put a CH3. So here's an H, here's an H, and here's an H. Perfect. On carbon 3, we're going to put a CH3. I'm just going to put it down here because it just makes it easier that we're not kind of crashing into each other. Okay, perfect. Remember, it doesn't matter whether it's on the top or the bottom, as long as it's on that carbon. We now need to finish off all our hydrogens. 1, 2, 3 here. This has 1, 2, 3, so it needs 1. This next one, carbon 3, has 1, 2, 3, so it needs 1. Okay, I don't need to put it in. This needs 1, 2. This needs 1, 2, and this needs 1, 2, 3. Okay, I want to get rid of that just so that it doesn't look so crazy. Okay, so let's kind of take a look at what we have. So 2, 3 dimethylhexane. Before we move on to the next slide, I want us to stop for a moment and actually look at what we've created. So I don't know if anybody noticed, but we learned something very early on. And we've created something called an isomer. Yes, okay. So let's look. Let's prove to ourselves that we've created this isomer. In order to figure out whether or not we have an isomer, we have to find the same molecular formula, different structure. These are definitely different structures. Let's count our carbons. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 carbons in this one. Let's count our hydrogens. 1, 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yes, I'm making a little mess of it, but I want you to see me actually counting. Okay, this next one. 1, 2, 3, 4, 5, 6, 7, 8. Oh yeah, C8. And then I promise you, if you count all the hydrogens, it will be 18 hydrogens, okay? And you're more than welcome to kind of do that for yourself. Okay, wow. Same molecular formula, different structure. We've created 2 isomers without even knowing it. Okay, let's move. So that is taking the name and drawing the structure, which I find to be actually easier than the other way around. But it really doesn't matter. It's just a skill that requires maybe just a little bit of a different way of looking at it. So what we've done for this one is we're giving you the structure, and I need you to name it. So there's some steps here for us to accomplish this properly, and they're really similar to the steps in naming it, or in drawing it, I should say. Okay, so we're going to do a IUPAC name for this organic compound in this structure. Oh, I want you to be able to see this. So if you notice, this has a bunch of carbons, and there's definitely some side chains. The IUPAC name is just the proper name for us to all in the scientific community name compounds the same way. There are many compounds out there that are named in the common way, and that's not wrong. It's just if you're going to speak to somebody in the scientific community, if you're going to publish any research, it needs to be in proper IUPAC form. Okay, so the first step is find the longest continuous chain of carbon atoms, and that's going to be your parent chain. You're going to name it, and this is your main branch. It helps to circle it, and so that's super, super, super important. Okay, next. So we are, what do we mean by the longest chain? So I want to do a little thing for you so that you can actually see what I mean by that. I'm going to find the longest continuous. So I'm going to take this and I'm going to start counting. So carbon 1, 2, 3, 4, 5, 6. Well, that's obvious. Okay, but let's see if we could find a longer one if we turn or twist, because continuous just means that they need to be in a row. So let's do this way. So I'm going to do 1, 2, 3, 4, and I'm going to turn 5. Well, that's not longer than 6, so that doesn't fit our bill. But let's keep going. Maybe there's something else. 1, 2, 3, and I turn 4. No. What about this one? 1, 2, 3, 4, 5, 6. Oh, that's a 6. So I have 2 6s right now, but nothing more than a 6. So here's what I want to say to you. When you're trying to figure out who your longest continuous chain is, don't worry. Pick the one that's obvious, right? Don't pick the one that turns, but it should be the longest continuous. Sometimes that could be one that's turning. So there it is. That's our parent. 1, 2, 3, 4, 5, 6, which means the name is hexane. So that's the parent name. Okay. Second, identify the side branches, right? The alkyl groups attached to the parent chain. It helps to circle them, name them, add dies, tries, whatever else you need, if it appears more than once. Okay, so here and here. So those are our side chains. This is a 1 carbon chain, and so that's a methyl. And this is a 1 carbon chain, so that's a methyl. Okay. So I have 2 methyls. All right, well, so if I have 2 methyls, then that's going to be dimethyl. Okay, why dimethyl? Because there's 2 methyls involved. And where are those methyls, right? So we're going to start finding the, we're going to number the parent chain, and we're going to number from the end that gives the branches lower numbers. All right, so this applies. Remember, we have to kind of go and count from left to right and then right to left and try and figure out which one gives us the lower number. Well, starting from the left, 1, 2. Okay, so I hit something at 2. If I start from the right, I'll get 1, 2, 3, 4. I hit a 4. And that's no good. I don't want that. 4 is a lower number than 2, obviously. Okay, so where is it? It's on carbon 2. And it's also on carbon 3. So the name for this would be 2,3-dimethyl hexane. Okay, and that's how we would kind of go about it in a different direction. Okay, let's keep going. Here are some other structures. So let's name these. These are branched hydrocarbons. So let's do this. Okay, so longest continuous chain. So I'm seeing 1, 2, 3, 4, 5. Okay. Now, could I have done this? 1, 2, 3, 4, 5. I absolutely could have. But that's just going to cause confusion for your eyes. And right now, if the longest chain is the one that's kind of straight in a row, do it. That's the one you want to circle, right? Why make things more confusing? So 1, 2, 3, 4, 5 means the ending here, the parent's name, is going to be pentane. And there's single bonds all the way through, right? So pentane. Here is my side chain. I'm going to identify it. It's a methyl. So this is a methyl pentane. Where is this methyl pentane? Well, I'm going to find the lowest number. I'm going to count from the end that gives me the lowest number. So 1, 2. So that gives me 2. If I counted from this end, I would get a 1, 2, 3, 4. I don't want that. So this is a 2-methyl pentane. Right? So super, super easy, I think. Obviously, it's going to require some practice, so don't worry if it doesn't all come to you all at the very beginning. All right, next. Longest continuous chain of carbons. So I'm looking at the one that's going all the way across. So 1, 2, 3, 4, 5, 6. If I tried to do, this one, the one that goes up and down. So 1, 2, 3, 4, 5. That's not enough, right? So there's nothing that we can do where it would not actually be longer. So the one that's straight across, typically we're not going to give you anything too crazy. But there's definitely ones that are challenging ones that might be out there. Here's our side chains. All right, so now let's do 1, 2, 3, 4, 5, 6. So we did our 6 first. So our 6 is going to be hexane. Okay, now what have we on each one of these? This is a methyl, and this is a methyl. All right, so how many methyls? I got 2. So dimethyl. So this is dimethylhexane. I can't stop there. I have to identify what number. So I'm going to count 1, 2, 3. Yep, I got them on there. If I count from the right, I'd get 1, 2, 3, 4. So no good. So on carbon 3, I have a methyl. And on carbon 3, I have another methyl. Do I have to write both numbers? Yes. Each methyl gets its own number. Okay, very important. Even if it's the same number, each methyl gets its own number. Okay, excellent. That's drawing. So now let's do the opposite, right? So that was giving the name from a drawing. Now we're giving the name and we have to draw it. Okay, so let's start with the parent name. So don't forget, right? The parent is all the way at the end, and that's hept. Hept is a prefix for 7 carbons. So we're going to do 1, 2, 3, 4, 5, 6, 7. Excellent. All right. Heptane, so all single bonds, so we don't have to do anything else. Let's move over and look. We need to place a methyl and we need to place an ethyl. So we need an ethyl on carbon 3 and we need a methyl on carbon 4. Because we're drawing this, our carbon 3 will be from left to right, right? And so this will be our carbon 4. So on carbon 3, I need to place an ethyl. An ethyl is a 2-carbon alkyl. So I'm going to have 1, 2. And then 1, 2, 3, 4, 5. So those are all going to be hydrogens. Okay, so this is my ethyl group. And I've placed it on carbon 3. Okay, on carbon 4, I need a methyl group. And that's going to be a CH3, right? To not confuse things with not too many hydrogens, I'm kind of leaving them off. That doesn't mean that you get to leave them off. It just means that that's what it would look like, okay? Because sometimes it just makes it easier. Okay, so this is a methyl group, and that methyl group is on carbon 4. All right, let's place hydrogens, because if we left it like this, which a lot of people do, it would be wrong. So 1, 2, 3, 1, 2. This carbon 3 has 3 bonds already, so it only needs 1. This carbon 4 has 3 bonds already, so it only needs 1. This needs 1, 2. This needs 1, 2. This needs 1, 2, 3. So there's a lot there, right? That's a lot going on. That's a hefty one. But it follows all the rules, right? And so that's what's nice about it. There's rules to this, and there's some common sense almost, right? Once you kind of follow the rules, you go, oh, yeah, I got this. Okay, next. 2-methylbutane. So butane is the parent chain. So we're going to draw that first. So 1, 2, 3, 4. Excellent. 2-methyl. So on carbon 2, so I'm going to make this my carbon 2. I'm going to put a methyl group. A methyl group is a 1-carbon group. I need to put all my hydrogens around. If you leave it like this, it is incorrect. So 1, 2, 3, because those are all hydrogens. Here, I'm actually going to put them in here since this won't be too bad. This will be 1, 2, 3. So hydrogen, hydrogen, hydrogen. This will be 1. This will be 1. This will need 1. This needs 1, 2, 3. Okay, so that is what 2-methyl-butane looks like. Okay, let's keep going. So let's retrace back to isomers now that we have a little bit of a knowledge of kind of how to make an isomer and what an isomer is. So we're going to take C5H12. So that's our molecular formula. And we're going to draw a bunch of isomers. Remember, this follows the CnH2n plus 2 format. So it's an alkane. All right, so we know how to draw alkanes. They're these straight chain substances. So if I'm going to draw 3 isomers, I'm going to draw my most simplistic one first. C, 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 so 5 C's in a row. And I'm going to put hydrogens all around. And with single bonds, I should get 12. All right, so what did we just create? We created an alkane with 5 carbons. So we created pentane. Okay, nothing fancy, no numbers, no nothing. Pentane, that was our simple one. Okay, now we need to create isomers. In order to create isomers, we have to actually pop off one of these carbons at the end, and we have to place it somewhere else. We're not allowed to lose hydrogens, lose carbons. We have to just place what we have in a different order. It's kind of like playing with Legos and you take them apart and you build something new, but you have to use everything. Okay, so this is what I'm going to show you a couple of things that I know that kids get wrong, and I want to make sure that you don't do this. So we have 1, 2, 3, 4. So let's say you do this. You're going to do 1, 2, 3, 4. I'm going to pop off that 5th carbon, and I'm going to put it here instead. All right, now I want you to notice how this is not a new structure. Okay, why? Well, if you notice, I can still make a long continuous chain of 1, 2, 3, 4, 5 carbons. You, in drawing it, decided to turn it. That doesn't mean that it's different. That just means that you drew a different flat 2-dimensional picture that actually isn't different structurally. All right, it's still going to get the same name as pentane because that's the longest continuous chain and there's no side branches. Okay, so that is incorrect. You need to actually make it look different. So 1, 2, 3, 4. Yes. And we need to take that carbon and not put it on one end or the other because that will just that will make a continuous chain. We need to pop it on one of these other carbons. So we're forcing it to become a side chain. Okay, so what we just put on there was a methyl group. And now let's put in our hydrogens. So 1, 2, 3, 1 here, 1, 2, 1, 2, 3. Okay, I want you to stop and actually make sure that it's C5H12. So we have 1, 2, 3, 4, and then 5. So that's C5. And then we have 1 hydrogen, right? So where's my hydrogen? Oh, no. Okay, we have 1 hydrogen right here. Hold on. Whoops. We have 1 hydrogen here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So yeah, it is C5H12. Not only that, but it has a whole new name, and that's kind of how you know you've created something if you're ever confused. Can I name it differently? Yeah, all right, it's a different structure. So this is 1, 2, 3, 4. So that's butane. And you'll notice the main chain, 1, 2, 3, 4 is the main chain, and then this is our side chain on carbon number 2. So that's 2-methyl-butane. Okay. Now, we still have 1 more isomer we can draw. So we need 3 isomers here. So let's keep going. Let's see if we could figure something else out. So let's pop off this carbon like we did, and let's move it. All right, I'm going to show you another wrong thing that people do. So we have 1, 2, 3, 4. Let's put the carbon over here, right? Boop, 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 boop. Okay, so why is this wrong? Well, It looks different, doesn't it? But what did we say about structures that you can flip, and when we start counting it and naming it, if it has the same name, it's the same structure. But you're going to say, hey, that's 3-methylbutane. No, it's not, because I would start counting from here. So 1, 2, right? And the 2 would give me the smaller number. So this is actually 2-methylbutane, just flipped to look like that. Okay, or vice versa, however you want to view it. So that is actually not a real structure. All right, so what are we going to do? Well, we have to utilize that pop off a carbon kind of thing. The best thing for you to do is just to recreate a different base, okay? Because that helps. So what do we mean by recreate a different base? Well, instead of a butane, why don't we just do 1, 2, 3? Why don't we pop off 2 carbons? We can do that, but we have to make sure that they are different, right? So far we did 1, 2, 3, 4. We still need another carbon to place. So I'm going to place it down here. Remember, if I place it over here or over here, I'm just making a butane again. And so I don't want that. So I'm going to put it right on top and on the bottom. Okay, so what that created when I put in all my hydrogens, so 3 hydrogens there, 3 hydrogens there, everybody else was good, is I created now a propane. And I created 2 methyl groups on the propanes. So these are dimethyl propane. And what are our numbers? Well, they're both on carbon 2. So this is 2, 2 dimethyl propane. Okay, I don't like how messy that is, and I want to make sure that it is clearer to you. So 1, 2, 3. And then on this carbon, which is carbon 2, I got my 1, 2, 3. And on this carbon, I have my 1, 2, 3. This center carbon has all 4 bonds. This one needs 3. This one needs 3. So it looks funny. It almost looks like a T, right? A perfect T. So that's 2, 2 dimethyl propane. And it adds up to 1, 2, 3, 4, 5 carbons and 12 hydrogens. You don't believe me? Count them, right? Stop the video and count it. Okay, next. So this next thing is a challenge, a little bit more of a challenge. What if we add a double bond and an alkyl group? What happens? So as you start learning more and more about all the variations that can occur, you're going to get more and more different structures. And how do we name these things? So this is a challenge. This is definitely not Regents material, but I thought, hey, let's kind of push this and let's see if you can handle it. All right, so the first thing that we do is we notice that this is not drawn exactly the way the other ones were drawn, and that's because what they did was they put CH3, right, and they just kind of collapsed it. Then they did a CH2, and then they did a C with a CH3, okay, and then they did a double bond with a CH2. Okay, so that's what this is. All right, so how do we name this guy? We're going to find the longest continuous chain of carbons, always the same method. So 1, 2, 3, 4. So there's my 4. And you also want to, if there's a double bond, you should include that in your longest continuous chain. There's actually a priority list of what should be in there, and any double or triple bond always takes priority over anything. Okay, so once I do that, I have 1, 2, 3, 4. That makes this the side chain. So 1, 2, 3, 4 gives me bute, but not regular bute, it's butene. Okay, butene is showing a double bond. So where is that double bond? Because remember, we can give numbers for double bonds. So the double bond, instead of counting from left to right, we're going to count from right to left. Okay, why? Because that's going to give us the smallest number. It's going to give us a 1. On carbon 1, there is a butene. So we say 1-butene. Now that would be just plain old 1-butene. However, we have this side chain here, and this side chain is a methyl group. So we're going to keep adding to the front of this. So this is methyl 1-butene. However, where is that methyl? It's on carbon 2, because it could have been on carbon 3, right? It wouldn't have been on carbon 4, because if we put it on carbon 4, it would just continue the long chain. Okay, so 2-methyl-1-butene is how we would handle that. Not bad, right? It's got two things going on at the same time. All right, what about this? So 1, 2, 3, 4. So once again, we got a butene. So I'm not going to redraw this because you can if you want, right? If it helps for you to see it. So this is also a butene. Okay, where is that butene? Well, once again, I'm going to start counting on the side that gives me the first kind of interaction of something happening. And so 1, so that's 1 butene. Same thing as the one right next to it. Except the CH3 now is not on carbon 2. It's going to be on carbon 3. So on carbon 3, we have a methyl. And so that's 3-methyl-1-butene. All right. What are these two structures to each other? We have 2-methyl-1-butene and we have 3-methyl-1-butene. If you remember, they are isomers of each other. Okay, why? Well, if you look closely, you're going to see 1, 2, 3, 4, 5 carbons. You're going to see 3, 4, 5, 6, 7, 8, 9 hydrogens. If you look over here, you have 1, 2, 3, 4, 5 carbons. You have 3, 4, 5, 6, 7, 8, 9, 10. Oh, did I count that wrong? I think I counted that wrong. I thought that was wrong. Okay, so let's do 3 and 3, 6, 7, 8, 9, 10. We have 3 and 3, 6, 7, 8, 9. Something is wrong there. Ooh, I know what's wrong. This should have a hydrogen on this. Ooh, that is very wrong. There should be an H here. Okay, so make sure you put that. I just realized that was incorrect. So those of you that might have been wondering what is happening, let's fix that. Okay, so let's do this. So this structure should have, so it only has 3, so this structure should have another H on it. Okay, now how is that wrong? Look, 1, 2, 3. Boop. So we need to make sure we fix that on our notes. Okay, does everybody see that? All right, so you noticed, oh, there was something wrong. They weren't isomers, but they are. The structure wasn't drawn correctly. So there are 5 carbons, and then there's 3 and 3 is 6, 7, 8, 9, 10. Okay. Wow, definitely something wrong with that. Thank goodness I noticed that. All right, next. Multiple double bonds. All right, so what happens if we have multiple double bonds? Well, we kind of employ the same ideas. If there's 2 double bonds, we're going to put the prefix di. If there's 3 double bonds, it's tri, and so forth and so on. So let's look at this. So you'll notice the longest continuous chain is 1, 2, 3, 4. Yeah, they're up and down, but it doesn't matter. That's actually showing a little bit more of the angles in real life and things like that. It doesn't matter. How you draw it on paper is never going to be a realistic interpretation unless you're a great artist. Okay, so 1, 2, 3, 4. So this is a butane, bute, I apologize, 4. Then there's a double bond, and then there's another double bond. So we see a double bond, and then we see another double bond. So that's 2 double bonds. So that's a diene. Oh. And then because this is weird, butadiene, they actually throw in an A. So butadiene. All right, but we can't stop there because those double bonds can be anywhere on the chain. So we have to acknowledge what's happening. So they've actually numbered this already. So 1, 2, 3, 4. And so on carbon 1, there's a double bond. On carbon 3, there's a double bond. So that would be 1,3-butadiene. So I want you to just notice one other thing. Why are they doing it from left to right? Well, they could actually do it either way. It's not going to make a difference. 1, 2, 3, 4. I'd still have 1, right? There's my double bond, and 3. So in this case, in some cases, it doesn't matter where the double bond is. Okay, next, let's look at this guy. So this is a CH2, C, C, and then a CH3. So we're doing longest continuous chain, and there it is. Notice all the carbons are attached to each other. If you don't like that, you can redraw it, right? So H, H, if you don't like the way that looks, boom, boom, and then kind of see if that makes sense. Boom, boom, and then C, and then this is H3. They're all connected. Okay, so important, right? But you don't have to redraw it. So here we go, 1, 2, 3, 4. So once again, this is a but, and it's a diene. Butadiene is what we say. And where is this? Well, we're going to count from left to right, and the reason why is because if I count from right to left, I won't hit something until I get onto carbon 2. But if I count from left to right, I hit something on carbon 1. So this is 1, 2 butadiene. All right, and 1,3-butadiene is an isomer of 1,2-butadiene. So if you don't believe me, count up all the carbons and the hydrogens, and you will see they have the same molecular formula, different structure. Okay, so for a little bit of fun to wrap this up, I wanted to show you this little cartoon now that you kind of understand how to name things. And you'll notice there's 2 double bonds in here, right? So we're going to call that a diene. So this poor molecule is saying, help, save me, I'm dying, right? He's drying. He's drowning, I apologize. Over here in the lifeboat, we got a little lifesaver kind of thing, right? You'll notice 1, 2, 1, 2, 1, 2. So this is not a diene, this is a triene. So he's saying, I'm trying. He's trying to save him. All right, hopefully that gave you a little chuckle. And that is topic 3.